So, welcome to the session again. We have already done very good number of problems in solid state chemistry, each problem covering some one particular logic, and as we were thinking, we have to switch over to crystal defects. So, crystals will form with some defects. You can't expect an ideal crystal. I think in one of the problems we have seen, in this particular problem, in the previous session we have already discussed something. See, actually the formula weight is this much, the formula weight is this much, 60.23. It adopts a rock salt structure. So, as soon as you listen rock salt structure, we think of 4 formula units per unit cell, because each unit cell has 4 anions and 4 cations, and it should become a habit for the students. So, 4 units are expected and each unit has 60.23 molar mass. We want molecular mass, so Avogadro number into edge length is given. So, from which you can get the volume, but that is in angstroms, 4 into 10 power minus 8 cube. This way you can calculate the density of the crystal. Density of unit cell is the density of the solid. So, if you calculate this, how much you got? Of course, this goes 10 times and all. So, 64 you will get 100 by 16, which gives 6.25 grams per cc. 6.25 grams per cc would have been the density had it been an ideal crystal. But at the same time he gave the density also 5 grams per cc. Instead of 6.25, why should it be 5 grams? So, there is some mass missing. Once there is a drop in density, what does it mean? Some mass is missing in the rigid volume. So, the drop in density corresponds to the missing mass. What do you mean by missing mass? Some ions are missing from their usual places. They are not crystallized, but the crystal dimensions and unit cell dimensions remain the same. So, how much drop is there? 6.25 minus 5, 1.25 drop is there out of 6.25. So, this much drop out of 6.25 corresponds to the percentage of ions missing. %20 of the ions are missing from the lattice. Actually, this can be otherwise calculated. Don't put 4. Don't put 4. Why did you keep 4 here? Because we know the rock salt structure. At the same time, in the problem itself, what is he telling? Some pairs are missing. When some pairs are missing, it is not 4. So, find out how many are there using the given density. That is another method. So, do not keep 4. So, 5 grams density is given. So, some effective number of formula units are there in the defective unit cell, and 60.23 by 6.023 into 10 power 23 into 64 into 10 power minus 24, 4 angstroms cube. So, this gives me, this goes 10 times. So, 23, 24 will give 10 again. So, this is going to be x into 100 by 16. So, x is going to be 5 into 64. 5 into 64 by 100. This is 20 and this is 3.2. So, what did you get? X has 3.2. So, 3.2 formula units are there per unit cell. In an FCC rock salt structure, you expect 4 formula units, but how many on average formula units are there? 3.2, means 0.8 missing on average per unit cell. So, per unit cell 4 formula units, 3.2 is there, 0.8 missing. So, missing pairs 0.8 by 4 into 100, this is going to give me 20%. So, 20% is the missing pairs. In this particular problem, what we should understand, in general in ionic crystals we can't expect an ideal structure. While crystallizing based on the conditions, some ion pairs will be missing while crystallizing itself. So, there are various varieties of defects we come across. Every time the defects need not be of same type. Sometimes some planes will not be formed, sometimes one line of ions will be missing, sometimes some ions only will be missing from lattice points. So, we have got plane defects, 3-dimensional defects, 2-dimensional defects, sometimes point defects, we call them sometimes interstitial spaces defects. What do you mean by interstitial spaces? Suppose in a crystal, in a crystal you have some ions neatly arranged. This is ion, this is another ion, these are ions, but there will be some space unoccupied. That unoccupied space is called interstitial space. We expect a space there in the crystal, we expect a space in the systematic arrangement of the ions. Suppose someone joins there, in the space some ion you find, that is unusual ion, that is unusually joined there. As per the ideal crystal there should be nothing, but one ion has joined. So, that is not a lattice point, that is a space. Interstitial space is also filled. So, we call it interstitial defect. So, we have got some lattice point ion is missing, that is called point defect. So, like this there can be a variety of defects. Defects are natural, and sometimes we ourselves introduce defects. Some defects are introduced into the lattice for some purpose. So, for some good purpose, defects are induced, defects are added to the crystal to obtain some special properties. Of course, we call it doping, that also we will see in the discussion. So, coming to, I think we have done pretty good problems on this. What is the distance between two vertically aligned spheres? This you should always keep in mind, ABC, ABC. This is ABC, ABC. From this and this, what is the distance? And that is nothing but, in the face centered cubic unit cell, the corner and corner, both corners, corner and corner, and this distance is what should I say, the distance between this sphere and this sphere. That is what he is asking, first layer and fourth layer, and this is side, front, bottom, these three together make a layer, top, back and left will make a layer. So, A layer, B layer, C layer, A layer. So, this way you have got 4 layers, first layer and fourth layer he is asking, first and fourth layer. So, that is nothing but tetrahedral void, octahedral void, tetrahedral void, tetrahedral void, octahedral void, tetrahedral void. So, this distance is nothing but this distance, body diagonal root 3a. This also we have done, different varieties of looking into unit cell. What is the percentage of unoccupied edge length also we have done, like suppose you have a body centered cubic lattice, this and this are occupied, this is unoccupied space, that can be easily calculated, that is A minus 2R, and you have a relation between A and R, you substitute that, you can get this. See, this is another problem we have done. Oxide ions, all tetrahedral voids are occupied by M plus. It is like lithium oxide. In lithium oxide, what is the structure? All oxides make FCC lattice and all lithiums occupy the tetrahedral voids. So, if you have lithium oxide, all oxides make FCC and you have got lithium ions occupying all the tetrahedral voids, top and bottom, left and right, back and front. All the tetrahedral voids are occupied. All tetrahedral voids, where do tetrahedral voids lie? Inside, here, here. On the body diagonals, you will have tetrahedral voids. So, you can connect them like this and make a cube again inside. So, the tetrahedral voids lie on the corners of the inside cube. You have got all lithium ions over there. He gave anion cation distance, means what? This 1/4 body diagonal distance he gave. From that we have calculated the inner cube edge length. From that you can calculate the nearest cation distance. So, these are all quite common in solid state. We have already done this calculation, so I am not going into detail. Now, what are we going to think? So, we will remove some ions from this and try to appreciate the crystal. So, that removal missing is called defect. So, we are all solving all these problems based on ideal crystals. So, we will have to go to the defective crystals, crystal defects, sorry, you have crystals with defects. Actually defects, here I gave some defects which are naturally formed. I did not mention about what we induce. So, the defects can be of two types, intrinsic defects and extrinsic defects. The defects which are quite naturally while crystallizing defects are formed are intrinsic in nature, by nature they are formed. We are not introducing any defects in this particular classification. Now, in crystal defects we have got stoichiometric defects, non-stoichiometric defects. This is a very peculiar word what we learned, stoichiometric defects, stoichiometry in defects. Defects should have stoichiometry. What does that mean? Suppose a crystal is formed from ions, whatever constituent particles. So, when the crystal is formed, it is formed with defects. So, here you can think two things, are defects stoichiometric or the remaining crystal stoichiometric in nature. First of all, what do you mean by stoichiometric nature? The ratio of ions will be maintaining the original ratio of the ideal crystal. Suppose in sodium chloride, you have got sodium and chlorine in 1:2 ratio. In lithium oxide, lithium and oxide should be in 2:1 ionic ratio. So, like that, if you have aluminum sulphide, there should be 2 aluminiums and 3 sulphides. You have cuprous sulphide, 2 coppers and 1 sulphide, that is a stoichiometric ratio. If that ratio is maintained even after defects, we call it stoichiometric defect. So, defect will maintain stoichiometric ratio, even the remaining defective crystal also will maintain stoichiometric ratio. So, both will have stoichiometric ratios. So, stoichiometry of the crystal is not disturbed. Such defects are called stoichiometric defects, the stoichiometric in nature. Even after defects, crystal will maintain the stoichiometric ratio of the constituent particles. What about the other one? Non-stoichiometric defects. And because of these defects, what will happen? Because of these defects, once a defect is occurred, the crystal, what you expect, that ratio will not be there. Suppose you are thinking for 1 sodium there should be 1 chlorine. This is stoichiometric ratio, original stoichiometric ratio. Suppose you may find one crystal with more sodium and less chlorine. You may find a crystal with more sodium and less chlorine, then it is not stoichiometric. That is a non-stoichiometric crystal. So, you may actually in ferrous oxide you have iron and oxygen in 1:1 ratio. If in a crystal if there is less iron and more oxygen, then it is non-stoichiometric. In copper sulphide you have Cu2s, there should be 2 coppers and 1 sulphur. Suppose that ratio is not maintained, that is non-stoichiometric. So, in stoichiometric defects, stoichiometry of the crystal continues to be maintained. In non-stoichiometric crystals, the stoichiometry will be lost. The defects may be non-stoichiometric and the left out crystal also may be non-stoichiometric. So, that way we will have to think. In the stoichiometric defects, you have got 2 varieties, Schottky and Frenkel, Schottky defects and Frenkel. And let me remind you one thing, it is not plane defect or it is not a line defect, it is only a point defect. These all what we are discussing as per your academic standard what you are studying. We are speaking about only point defects. Point defect means what? Either lattice point defect will be there or interstitial defect may be there. So, in that first one is in the stoichiometric defects we have got Schottky defects. What do you mean by Schottky defect? In this particular defect, pairs of ions will be missing from their respective lattice points. What do you mean by pairs missing? Do not think after crystal formation is done, the pairs will escape. Do not think like that. Once crystal is formed, it is formed with defect. So, while crystallizing, the cations and anions are forming the crystal, some anions and cations will not get crystallized in their respective lattice points. That way you have to think. Suppose in Schottky defect you have got A plus x minus A plus x minus x minus A plus and x minus A plus, this is the healthy ideal crystal. This is a healthy ideal crystal, but while crystallizing some ions will be not crystallized, that is not crystallized, and some A is not crystallized. Here there is a vacancy, here there is a vacancy. Which ions are missing from the lattice? You see, between 2 A plus ions, one X minus should have been there, it is not there. Means what? It has not escaped, it has not come there. Similarly, between 2 X minus ions, we expect A plus, but that also has escaped. Escaped in the sense it has not crystallized over there. Now, here a very important point one should understand. Because of the missing of these 2 ions, the overall crystal will not lose its stoichiometry, because for every A plus X minus missing, there is one A plus missing. So, they are missing in the stoichiometry ratio, therefore, there will not be any damage to the stoichiometry of the crystal. But here what you should think, because a mass is missing from the bulk of the crystal and the crystal being rigid, volume is not changing, mass is decreasing. When some pairs are not formed, mass will not be there, there will be holes there, vacant places instead of ions. So, mass is missing, but as per the dimensions unit cell is developed, therefore, mass is less, volume is same, density will be less. So, due to Schottky defects, the density of the solid will be less, expected density will be something what we have done in one problem, that 60.23 molar mass problem we have just now done, 20% of the ions are missing. Because the ions are missing, there is a drop in the density. Suppose let us assume if the density is more than expected, what do you think? If the density is more than expected, how can a crystal have more substance than what it should be there? Maybe somebody has doped something in the interstitial spaces. That way you have to understand. Practical density more than calculated density, we should understand somebody might have doped some material in the interstitial spaces of the crystal. Suppose the density drop is there than expected, ideal density, you should understand some pairs of ions are missing. So, in Schottky defect there will be a drop in density and holes will be there in the place of lattice points. It's not an interstitial defect because nothing is happening in the interstitial spaces. Always remember, interstitial space means what? The space between the spheres. This is interstitial space, that there is nothing is happening. It is a point defect. Lattice point is not having an ion. And this kind of a defect is quite common in alkali metal halides, Alkali metal halides generally crystallize with some ion pairs missing. So, that is called a Schottky defect. Now, Frenkel. What do you mean by Frenkel defect? Suppose you have got A plus x minus, A plus x minus, x minus, A plus x minus. This is the actual crystal. This is the actual crystal, ideal crystal. But in some cases what happens, this A plus should have been crystallized there, small cation. Instead of that, what will it do? It will not crystallize there. Instead of that, it will come down and somewhere else it will be crystallized. It slides down. Do not think within the crystal the ion is slipping down. While the crystal is formed, instead of sitting in one particular place, A plus has settled in some other place. What is that some other place? It is an interstitial site. In an interstitial site it has settled. So, it is present in an unusual place. Actually, this is not a lattice point. See, there is nothing here. Here you see, there are gaps. That is not a lattice point. What is that called? Interstitial space. Keep 4 spheres like this. This is an interstitial space. So, some ion which is supposed to be here has slipped down to this place. So, because of that it will be missing there. So, it should have been there, it is elsewhere. This is an interstitial space occupied by some ion. Generally, small ions do this kind of a mischief. Silver plus in bromide lattice. In silver bromide ions are so big, so interstitial spaces are so wide, Ag plus being very small, it will slip down. So, it will slip down into interstitial site. Now, tell me, will there be any damage in the density? Because of such defect, mass is still there, mass is not missing, it is not going anywhere, but it is adjusting in some other space. So, there is no mass loss to the crystal because of this defect. If the same crystal has got Schottky defect also, there may be mass loss, there may be density loss. The density loss is because of Schottky defect, but not because of Frenkel defect. So, Frenkel defect will continue to be like that without affecting the density. Now, what kind of a defect it is? You can now call it a point defect as well as an interstitial defect. Schottky defect, ions are missing from the lattice points. In Frenkel defects, ions are missing from the lattice point, are appearing some other place which they are not supposed to occupy. So, interstitial spaces it is appearing, therefore, you can call it an interstitial defect as well as a point defect. We will see the visuals. After completing this, we will come there. Let us see. A plus B minus is the actual crystal. See, the entire line is missing, one line of ions. You can call it line defect as usual. See, the other ions are there, line defect. Anyhow, some pairs of ions are also missing. You can see that. So, vacancies. So, let us think there should have been a blue ion here, there should be a red ion. So, what is the ratio in which they are missing? One blue ion and one red ion are missing. So, they are missing in stoichiometric ratio and safeguarding the stoichiometry of the entire crystal. Now, what about this? Again it is a healthy crystal, and see that A plus is missing, somewhere else B minus is missing. So, this is Schottky defect. Because of this loss, there will be mass loss, density is equal to mass by volume. Volume is safe, there is inside density missing, mass is missing, therefore, mass by volume density will be decreased. So, this is how Schottky defect can be appreciated. Just see once again, see the ions were there, but do not be carried away by a feeling that they are missing from the salt, from the crystal. While forming the crystal itself, they will not come. Just to tell you that they are missing there, we have shown this visual. This is Schottky defect. So, there is a cation vacancy, there is an anion vacancy because of Schottky defect. So, they are in 1:1 ratio, stoichiometric ratio. Now, let us think of Frenkel defect. What do you mean by Frenkel defect? There will be ion crystallized in unusual place. See, this is a healthy crystal, this is a healthy ideal crystal. Now, if you assume a Frenkel defect over there, see what is happening, A plus is missing from its usual place. Let us see back, cation vacancy. See, this is actual crystal, this A plus should be here, instead of here it will join somewhere else, that is it, which it is not supposed to be present. See, here it is missing, so it is a point defect, lattice point defect. Here actually see the other places, it is an interstitial site, in that interstitial site there is an ion. So, it is an interstitial defect as well as a point defect. Be very clear about Schottky and Frenkel. In Schottky it is only point defect, in Frenkel it is interstitial as well as point defect. Ion is missing from lattice point, ion is present where it is not supposed to be present, and because of this density loss will not be there, because mass is still there, it has not come out of the crystal, the ion is still present in the crystal. So, the density will remain the same. Usually this is shown by silver bromide. Bromide is big and silver is so small, so it can generate, while crystallizing silver will be missing from the usual place, because being small it will join some bromide interstitial spaces. Now, within the ionic lattices there is one more variety of defects. These are doping defects. Actually, we do not check stoichiometry also here. And by the way, in Frenkel and Schottky, crystals will continue to be neutral. Why? Because one Na plus ion missing, one chloride ion will be missing. So, crystal continues to be neutral. In Schottky also there is no charge loss. So, the crystal continues to be neutral only, no crystal is charged, that you remember. Now, we will do a very interesting thing. So, this is an ideal sodium chloride crystal. I think in physics you learn, if any material has got some atomic holes kind of a thing, they can behave like conductors. There should be free electrons or there should be free holes. So, conductors are expected to have holes or free electrons like. Actually, in this crystal you do not find any cation vacancies kind of a thing in the form of holes. So, what we do while crystallizing sodium chloride, we add some strontium chloride also. While crystallizing sodium chloride, we add some impurity, strontium chloride, because the size of strontium plus 2 nearly matches, it can work out in sodium lattice, rock salt lattice. So, what will happen? Strontium chloride will bring chloride ions, sodium chloride also brings chloride ions. So, I want to make an FCC unit cell, and you all must know one FCC unit cell has got 4 chlorides. We have done this so many times. FCC unit cell means corners and faces are occupied by ions. So, corners are occupied by chlorides, faces are also occupied by chlorides. 8 corners, 8 into 1 by 8, 6 faces, 6 into 1 by 2. So, put together there are 4 chloride ions. So, 4 chloride ions can make one unit cell of FCC. How many octahedral voids are generated? We have done 100 times so far. N atoms make an FCC lattice, there will be n octahedral voids, 2n tetrahedral voids. So, n chlorides can make n octahedral voids, 4 chlorides can make 4 octahedral voids. So, how to produce 4 chlorides? Either you should take 4 sodium chlorides, 4 sodium chlorides can give 4 chlorides which can make one FCC unit cell, which can make one FCC unit cell. 4 sodium chlorides can have 4 chlorides, 4 chlorides can make one FCC unit cell like this. Now, I won't bring 4 sodium chlorides, I will take 2 sodium chlorides and sorry, 1 strontium chloride. So, 2 sodium chlorides and 1 strontium chloride. 2 sodium chlorides will bring 2 chlorides, 1 strontium chloride also brings 2 chlorides. Put together you have got 4 chlorides which can make what? One FCC unit cell. One FCC unit cell of 4 chlorides is generated from where? 1 sodium chloride and 1 strontium chloride. Now, in one FCC unit cell how many octahedral voids will be there? 4 octahedral voids. There can be 4 octahedral voids. Now, do you have 4 ions to fill the octahedral voids? You have got only 3 ions, 2 sodium ions, 1 strontium ion. Chlorides have come, 4 chlorides, but 4 ions are not there, cations. You have got only 2 sodium ions and 1 strontium ion. Had it been a healthy sodium chloride crystal, what would happen? 4 chlorides make 1 FCC unit cell and all the octahedral voids are occupied by sodium ions. But here 4 chloride ions make FCC unit cell, there are 4 octahedral voids, but there are only 3 ions. Means what? One of the octahedral void will not be occupied. So, you are successfully creating one hole. So, which makes the crystal conductor, that we will see now. This is called ionic doping, that is it. Instead of 2 sodiums, you have got 1 strontium, because of which 1 sodium place is left vacant. So, in the lattice there is a vacancy created. So, there are 2 sodiums which are supposed to be crystallized. You have introduced strontium chloride. So, out of 4 chlorides, 4 octahedral voids are there, but you do not have 4 sodiums. You have got only 2 sodiums and 1 strontium. So, 2 sodiums will go and 1 strontium will go into octahedral void, 2 sodiums will join 2 octahedral voids and 1 octahedral void will not be occupied. So, you will get a vacancy over there. So, instead of 2 sodiums, you have got only 1 strontium and there is a vacancy created. So, in ionic crystals you can have some vacancies and make them conduct. That is one technique how we introduce some defects. Purposely we do it. I told you in the beginning, intrinsic defects and extrinsic defects. This is the defect what we have introduced. So, these are the things. Coming to the second variety of defects, non-stoichiometric defects. Non-stoichiometric, we have done stoichiometric. Now, it is non-stoichiometric means because of the defect the stoichiometry of the material will be lost. Stoichiometry means what? The cation anion ratio should be an ideal ratio, but that ratio will be missing because of some phenomenon. So, in non-stoichiometric defects, you have again two varieties, metal excess, metal deficient. Metal excess and metal deficient. What do you mean by this? There should be cation anion ratio. Other than that ratio, extra cations are present, that is metal excess. Metal deficiency, other than that ratio, less metal atoms are present, that is metal deficiency. So, how can that happen? The students may think if some metal ions are missing or some non-metal ions are missing, like that if you think, the charge of the unit cell will not be maintained neutral. Even though there is metal deficiency, even though there is metal excess, unit cell will remain neutral. So, what is the phenomenon? How does this happen? That we should understand. So, before going into visuals, first let us try to understand. Suppose I have got some sodium chloride lattice like this, a very simple understanding, chloride and sodium plus, chloride, sodium plus like. So, this is an ideal healthy crystal, this is an ideal and healthy crystal, but while crystallizing exactly equal number of sodiums and chlorides got crystallized. Suppose there is excess sodium gas is used to crystallize this, what may happen? Suppose excess of sodium vapors are passed through it. While crystallizing. So, what may happen? The sodium vapor gets ionized into sodium ions and electrons, So, that electron will behave like chloride, sodium ion will go to sodium place. In sodium chloride crystal, you have cation places and anion lattice points. In the cation lattice points, cations are supposed to occupy, anion lattice points, anions are supposed to occupy. But here you have got good number of sodiums and chlorides in equal proportion, but you have got some extra sodium. So, that extra sodium while crystallizing will get ionized and form Na plus and electron minus. So, that Na plus and electron minus also will go into the crystal, sodium plus will join cation lattice point and electron will join anion lattice point. So, the crystal will not be like this. So, it will continue somewhere like this. Here you are supposed to having Na plus, here there should be chloride minus, you will have electron, and here again chloride, here again sodium. So, here again sodium, here again chloride. So, in this particular unit cell, I mean lattice, complete lattice, you have got sodium chloride in good proportion, but somewhere in the crystal you will have one sodium plus and one electron trapped. This electron is generated from sodium only. So, one plus is developed, one minus is developed. Now, sodium joins the sodium's place, electron joins chloride place, because you have sent only sodium. So, electron is trapped in the environment of 4 sodiums. So, there will be balances of the forces. So, electron will not escape out of the crystal. So, it will stay there only. It is rather a trapped electron captured in the crystal. Trapping happened. The electron is trapped in anionic lattice point. It occupied chloride's position. And once you have electrons trapped in the crystal, it will behave like a conductor. So, that sodium chloride solid will now start behaving like a conductor. One more point, it will now develop some color, the crystal will develop color, not only here, somewhere else. Suppose the sodium is not there, suppose this chloride is not there, there may be some electron trapped. See, electrons are trapped here and there. Because of such electrons, it may behave like a conductor. Point 1. Point 2, such centers are called F centers. Farbengenter means color causing center. The electrons in this particular environment start vibrating and there will be energy levels created. For that excitation, electrons would require a part of visible light. So, once they catch up wavelengths of visible light, the crystal will start showing color. This particular sodium vapor blown over sodium chloride while crystallizing, you will get yellow colored crystals, golden yellow colored crystals. Those crystals are formed because of the trapped electrons, because of the F centers. And like this you will have even potassium chloride with excess potassium while crystallizing. So, potassium while crystallizing will ionize into potassium ions and electrons. Electrons are trapped in the anionic lattice points and that also will show color, because that is potassium environment, not sodium environment. It will show some other color like lilac, it shows excess potassium over potassium chloride. Excess lithium over lithium chloride would give pink color crystals. Why the color? Color is because of the trapped electrons in the lattice. So, why different colors? The energy levels are not same. The energy levels that are developed in the F centers may not be same. So, the absorption of visible light may change based on absorption, the wavelength of visible light being absorbed, a system will show some color. So, in all these crystals, metal is excess metal is entering into the crystal. So, that is the issue. See, this is the ideal crystal. Sodium gets ionized into sodium plus and iodide minus. See who is escaping? That is it. I will repeat. Ideal, instead of B minus, see sodium ionized as sodium plus and electron. See that instead of electron, instead of anion, electron is trapped between 4 cations, you see in this 2D lattice. In this metal excess, see A plus ions are more, in the place of B minus electron is there. So, what do we call it? Metal excess defect. Now, are A and B maintaining stoichiometric ratio? No way. A is more, B is less. You do not call it sodium chloride, sodium 1 plus X chloride. There is some extra sodium. The electron will occupy some anionic void, anionic place. So, this is metal excess defect. Now, coming to metal excess defect, there is one more: sodium excess in sodium chloride, potassium excess in potassium chloride, lithium excess in lithium chloride. This is yellow, this is lilac, this is pink. The color is due to what? F centers, that we have already discussed. There is some other beautiful example for metal excess defect, zinc oxide. This is originally a white crystal, but when crystallized in very hot condition, what will happen? Let us see. Zinc and oxygen, zinc should transfer electrons and it should form Zn plus 2 and it should form O minus 2. It should form O minus 2 and these two should get crystallized. Now, sometimes what happens in too much hot condition, when you start crystallizing it, the electron transfer will not take place to oxygen. The oxygen will remain outside the crystal. The electrons lost by zinc will occupy the place of oxygen. Suppose you are supposed to have this lattice. See, there should be oxide, there should be zinc, there should be oxide, there should be zinc here, there should be oxide, there should be zinc here. It should be like that, of course, oxide, zinc, oxide. This is how it has to be crystallized. Now, this O minus 2 comes only if electrons go to O. But in a hot condition, that oxygen may not take oxygen, some oxygens. So, instead in this place electrons are trapped, the electrons lost by zinc. So, what would you get? Instead of this, Electrons are trapped. Electrons are trapped in this environment. So, this is also F center, because of which the zinc oxide gets a yellow color. So, here who is excess? Oxygen is not there, there is less oxygen, more zinc. So, the formula will be zinc 1 plus X oxygen, metal excess. So, when you crystallize from very hard condition, sometimes electrons may be trapped instead of O minus 2. Even this happens. This is also a metal excess defect. Coming to metal deficiency defect. Metal deficiency. Metal deficiency means what? Less metal, more non-metal get crystallized. How can that happen? So, let us take a simple example. You have got iron oxide getting crystallized. You want to crystallize iron plus 2, oxide minus 2. So, it would require iron and oxygen in what atomic ratio? 1:1 atomic ratio, they are supposed to be crystallized. So, some iron less will get crystallized and oxygen is usually crystallized. Suppose you have 10 oxygens, there should be 10 irons. If you have 100 oxygens, there should be under 100 irons, but more oxygen gets crystallized and less iron gets crystallized. What would happen? Let us see. So, you have iron plus 2, oxide minus 2, iron plus 2, see oxide minus 2. Here iron is not crystallized, oxide. Here again iron plus 2, oxide minus 2, iron plus 2. Just see this. You have got 1, 2, 3, 4 irons. Of course, it should continue like that. It is a lattice, I should not count like that. There is some iron missing. What is there supposed to be? Iron plus 2. That iron plus 2 did not come. Some iron content is not crystallized. So, 1 Fe plus 2 should be compensated. Whether mass compensation takes place or not, none of our business. Charge should be compensated, because no crystal is charged. Crystals must be neutral. So, crystal must be neutral. Then who will compensate that plus 2 charge? So, while crystallizing, these irons will crystallize, instead of plus 2, they crystallize in plus 3 form. So, 2 irons will change their oxidation state to plus 3 state. 1 iron is missing, iron plus 2. In that place, the other 2 irons get oxidized. Actually, oxygen is oxidizing iron. So, some iron will get extra oxidized for the given oxygen. So, in that crystal, some of the irons will exist in the form of ferric, even though the lattice is that of ferrous oxide. 1 ferrous ion missing is compensated by 2 ferrous ions get extra oxidized into ferric. So, that plus 2 charge is now compensated here. So, this is in this case what is happening? Some iron is missing. So, metal deficiency defect, so metal drop. So, this is not metal excess. In sodium chloride, lithium chloride, potassium chloride, zinc oxide case, metal excess was there, electrons were trapped. Here electrons are not trapped, there is no need, there is a metal vacancy, that charge is compensated by other metal ions showing higher valency. Here what you should think, if you want metal deficiency defect to take place, metal should be able to show variable oxidation states. Can barium oxide show this? Suppose barium plus 2 is missing, will 2 other bariums show plus 3? No chance, barium cannot show plus 3 state. So, which kind of metal oxides will show this kind of metal oxide, metal sulphide will show this kind of metal deficiency defect? The metal should be capable of showing variable oxidation states, then only it is possible. Let us work out some nice mathematical approach in this particular defect. Suppose you have got iron 0.90, what do you understand from this kind of presentation? This is a metal deficiency defect. So, this being a metal deficiency defect, some iron is less. So, I put instead of 1:1, it is a non-stoichiometric crystal, iron 0.90. So, immediately we should understand there is less iron than expected as per stoichiometry. So, that iron exists in ferrous and ferric forms. So, all the nitrogen irons are not in +2 state, obvious. Now, let us take in another way. Iron, for every 9 irons, I multiply with 9, 10, I will get 10 oxygens. I just multiplied both with 10. So, what do you understand from this? 10 oxygens and 9 iron atoms are there in the form of ions, but crystal must be neutral. So, what is the negative contribution? -20. What should be the positive contribution? +20. Otherwise, crystal will not be neutral. So, out of 9 irons, some are +3, some are +2. How many are +3? How many are +2? Let us think X irons are in +3 state, 9 minus X will be in +2 state. So, X into +3 plus 9 minus X into +2, X into +3 plus 9 minus X into +2 must contribute +20 in order to neutralize the charge of 10 oxygens. So, this will be +20. So, this is going to give me 3x plus 18 minus 2x is 20. So, x plus 18 is 20, x is equal to 2. So, what do you understand? There are 2 irons in +3 state, there are 7 irons in +3 state. Out of every 9 irons, 2 are in +3 state, 7 are in +3 state. So, like that in metal deficiency defect, the lesser metal undergoes greater extent of oxidation partially and crystal is developed. This is also quite common. Now, we can actually work out like this 0. Actually this is a healthy crystal, Cu2s, ideal formula, cuprous sulphide. Suppose instead of this they give Cu 1.6s. What do you understand from that formula? Some copper is missing. So, copper can show which oxidation states? +1 and +2. So, out of that 1.6 coppers, some are in +1, some are in +2, cuprous and cupric. We can work out like this. Cu16 S10, because 1.6 and 1 I multiplied with 10. So, out of 16, x are in what state? +2 state. 16 minus x are in +1 state and should give -20. So, +20, because sulfur produces -20, this should produce +20. So, we can work out 2x and +16 minus x is 20. So, x plus 16, 20, x is equal to 4. What do you understand? Out of 16 coppers, 4 are in +2 state. There are 4 cuprous ions and 12 are in +1 state. So, it's nothing but natural that this can be shown only by the metal ions or metals which can show variable oxidation states. So, this is metal deficiency defect. Metal excess defect will develop electrons captured in the crystal. In the metal deficiency defect, there will be vacancies and that metal ion is compensated by higher oxidation states of other metal ions. So, that is shown by metals which can show a variable oxidation state. You can't expect a metal deficiency defect in barium oxide, strontium, like that, because they always show fixed oxidation states. So, this is metal deficiency defect. Sometimes we introduce defects. I think most of you are aware of conductors, semiconductors and insulators. Conductors means they can conduct electricity to a very good extent. Insulators, they resist so much, they possess lot of resistance, but semiconductors possess moderate conducting ability, means what? If you heat them, they start conducting. What is the mechanism? See, every material will have some electrons attached to the valency shells. So, we call all electrons as a group in a valence band, and for the electrons to move there should be a conductance band. So, in metals what will happen? The valence band and conductance band are almost in a overlapped condition. So, obviously once you apply some potential, the electrons will start moving. That is why metals are very good conductors, because valence band and conductance band will be close to each other, or almost they merge into each other. Very good metals it happens, I mean very good conductors it happens, but in insulators what happens? The valence electrons are tightly held to the material and the conductance band will be a bit high. So, electrons will not jump into conductance band. How much ever heat you supply, how much energy you supply, under practical conditions electrons can never enter into conductance band, you know. So, that is why rubber, paper, plastic, glass, those materials are mostly they contain more non-metallic content. So, electrons are tightly held to the material, the conductance band will be far off by means of energy. So, it is difficult to shift the electrons into conductance band. If valence band and conductance band are very close, that is metallic. If valence band and conductance band are very far, that is insulator. If valence band and conductance band are close enough, if you can excite by heating, that is a semiconductor. But we can't keep on heating whenever you require some conductance. So, for that what we do, semiconductors are converted into better conductors by introducing some defects. They are extrinsic defects. We will introduce the defects purposely. So, when you introduce a defect, the semiconductor will become a very good conductor. So, without heating also they start conducting. Rather you are converting this you can't do anything. The semiconductor is made into a better conductor by introducing some impurities in it. That phenomenon is called doping. Let us see some example. See that silicon crystal. Network pure silicon, beautiful solid. The beginning we decided network solids. Each silicon is bonded to 4 other silicons tetrahedrally, and this continues like this. So, this is a network solid. Each silicon is bonded to 4 other silicons. Now, while crystallizing silicon, I will add some impurity. There are 2 varieties of impurities what we can introduce. If you are aware, this is a 4th group element. It belongs to carbon group with 4 valency. Now, if you introduce a 3rd group element, 3rd group element cannot fit into this valency. 3rd group valency is only 3. So, what happens, one vacant orbital will be still unoccupied left there, which will behave like a hole. So, you can introduce holes into this particular material by introducing 3rd group element. See this germanium, again 4th group element. In that 4th group element he introduced arsenic. Arsenic belongs to which group? 5th group. 5th group, how many valency electrons will be there? 5. Arsenic, see arsenic here. Nitrogen, phosphorus, arsenic, antimony, bismuth. So, best suited doping in germanium crystal is arsenic. Arsenic has 5 valence electrons, but this lattice requires only 4 bonds. So, 1 electron is unutilized surplus electron for arsenic, and that arsenic will be here and there, wherever you have one arsenic atom distributed in the crystal, there will be 1 electron left unutilized. Now, the crystal has some free electrons. Once you apply some voltage, the electron you can have you can achieve electric current. So, you are making this crystal behave like a conductor, though it is originally a semiconductor. Germanium was originally a semiconductor. Now it is made a better conductor by introducing some impurity, arsenic, which belong to fifth group. So there is an extra electron. So such conductors are called N-type semiconductors. You have got a free electron over there. Suppose instead of fifth group, you introduce a third group element. So germanium, there is an indium introduced. See the difference. Arsenic belong which group? Fifth group. Germanium, fourth group. In fourth group metal, you have introduced fifth group metal. So there is an electron left, because fifth group valency is 5. It can use 4 bonds, 1 electron left unutilized. Whereas in the next case, again fourth group, but I have introduced a third group element. So third group element can form only 3 bonds. So there will be one unoccupied bond, orbital, you see, positive hole, there is no electron. This is called p-type semiconductor. So these are the defects what we have introduced. So there are some natural defects formed like Schottky defect, pair of ions will be missing, still the crystal will be stoichiometric. Frenkel defect, the small ions will slip down into interstitial sites, the density will continue. Stoichiometry is safe, crystal is neutral. Point defect and interstitial defect. Silver bromide is the best example for Frenkel defect. Silver bromide can show even Schottky defect. And Schottky defects are shown only by alkali metal halides. And in the metal excess defect, you can blow some sodium vapor during sodium chloride crystallization and achieve some metal excess defect with anionic vacancy, anionic lattice points occupied by electrons. So electrons are trapped in the anionic lattice points, so we call them F centers, so they get color. Excess potassium in potassium chloride, excess lithium in lithium chloride, that is all metal excess. In zinc oxide also, when zinc oxide is crystallized from a hot condition, instead of oxide, electrons will be trapped in the lattice, they are also F centers. So you can expect F centers in metal excess defect. The metal deficiency defect, you have got vacant places created by metal ions not crystallized, and their charge is compensated by further oxidation of the other nearby metal ions. So ferrous ion is missing, 2 ferrous ions get ferric ions. So charge is compensated, +2 charge is compensated, and the crystal remains again neutral. Always it is a golden thumb rule that no crystal is charged, whatever may be the defect. Once there is a defect, crystal will always remain neutral. If there are many vacancies inside the crystal will be very light, the density will be less. Coming to this doping, this introduced defects like strontium chloride introduced into sodium chloride. So instead of one sodium if you have only sodium chloride, for every 4 chlorides there will be 4 sodiums occupying the octahedral voids. But the 4 chlorides are coming from 2 sodium chlorides and 1 strontium chloride, but there are only 3 metal ions present, 1 metal octahedral void will remain unoccupied. So you will have a hole created in the crystal of sodium chloride. Purposely we do that. Strontium chloride is introduced into sodium chloride crystal. Just for imagination and logic sake, if you take sodium chloride and aluminum chloride are doped, just for the thing, not that it is really happening, for logic purpose I am telling. There are 4 chlorides can make one FCC lattice, 4 octahedral voids, but you have only 2 ions. So what will happen? 2 octahedral voids will remain unoccupied. So you have created 2 holes. This is called doping of ionic substances. And this doping is altogether very different. To convert a semiconductor into a better conductor, metals are anyhow good conductors. Materials made of non-metals, rubber, plastic, glass, paper, cellulose, they cannot be good conductors. They offer very good resistance. but silicon, germanium, these are semiconductors. Upon heating they can conduct electricity, but without heating, how to make them good conductors? By doping impurities. So, in the fourth group element, if you dope any fifth group impurity, there are electrons left. So, free electrons you have achieved, you got n type semiconductor. And if you dope third group impurity, that is indium in germanium, you got some vacant places developed, and you have got you have created holes that also can act as a good conductor. So, this is the beauty of solid state chemistry, and we have learnt so many aspects right from the beginning, and we have divided solids into amorphous and crystalline. Then we have divided crystalline solids into metallic solids, ionic solids, molecular solids and covalent solids, and we took 7 crystal systems, and we have analyzed cubic crystal system and hexagonal crystal system alone. Within cubic crystal system you have got primitive cube and face centered cubic and body centered cubic, and we have developed the parameters and crystal dimensions, and we have done so many calculations based on that. Then we have got some spheres closely packed, we have seen some patterns like ABC, ABC, AB, AB like patterns. We appreciated voids, void placements, void numbers, void sizes, and then we understood ionic crystals made of anions and cations being occupying the voids, or sometimes cations making the lattice, anions occupying the voids like calcium fluoride. Then we have come to crystal defects, and we have seen only point defects, not plane or line. Point defects, there we did stoichiometric and non-stoichiometric. Within stoichiometric we have seen Schottky and Frenkel. In non-stoichiometric defects we have seen metal excess defect and metal deficiency defect. Then we understood the doping also. So, all put together you can easily appreciate the subject like anything. So, just if you have any doubts, just go through the lectures again. Repeatedly we taught so many things, so almost they should clarify your doubts. And still if you have any doubts or any problem unsolved, we are always there. You can just send the message through 24/7 Yep platform. We are there to answer your doubts. We can also, if so many ask a single doubt, we can discuss in the class itself. Thank you. We will meet with the next chapter. Thank you.